Response to benzene and aromaticity chapter. This is a further continuation to aromatic compounds. The next in this series and in the syllabus for SYB form as per PCI syllabus is polycyclic aromatic hydrocarbons. That is more aromatic rings or benzene rings fused to benzene. And the simplest is naphthalene. And then we are also going to see anthracene, phenanthrene, etc. They are all aromatic. They follow all the rules of aromatic, like the de-Huckel rule and other things. So we proceed further for these PAH compounds, polynuclear hydrocarbons, and we are going to deal mainly with the synthesis, reaction structures, and medicinal uses of three main derivatives: naphthalene, anthracene, phenanthrene. We are also going to see some additional derivatives like diphenylmethane, triphenylmethane, and then we will wind up with the MCQs and various questions. Let us say what are the polycyclic aromatic hydrocarbons, also called as polyaromatic hydrocarbons or polynuclear aromatic hydrocarbons. Cycle or nucleus are the commonly used words in organic chemistry. That is why we call some rings with heteroatoms as heterocycles. So these are organic compounds, and these are purely consisting of carbon and hydrogen, and they have multiple rings fused to each other, and they are flat rings, and the electrons are as delocalized clouds, and they are 4n plus 2 pi electrons. We are basically going to see the simplest of these derivatives and some of their derivatives, of course, with some substituents. But we are going to morely deal with the basic skeletons, and the three basic skeletons have been identified. That is naphthalene, that is one benzene ring fused to another benzene ring. One more benzene ring fused is, of course, anthracene, and it's like three benzene rings fused together in a different fashion is phenanthrene. PAH are non-polar molecules because there is not much electronegativity difference between carbon and hydrogen, and therefore they are uncharged or non-polar compounds, and they are mainly found in coal and tar deposits. And when you combust some organic matter, whether it is fuel or any other wood or something, the end products are these PAH compounds. They are abundant in universe, and they have been found to be formed possibly billions of years ago, and they are very old to this Mother Earth, and they have been contributing to the significant percentage of carbon to this entire universe. And they are possible starting materials for the biological synthesis of materials required by the earliest forms of life. Let us see we are going to just study the source, structure, nomenclature, properties, synthesis, and reactions of naphthalene. This is naphthalene, one benzene ring fused to another. This is anthracene, one more benzene ring on naphthalene, all in one line. So this is a linear fusion. Phenanthrene is a structural isomer of anthracene, but the fashion in which the benzene rings are fused together is called as angular fashion. We are having also other derivatives which we are going to cover in the later videos, as diphenylmethane, medicinally very important, also called as benzhydryl, and we have triphenylmethane, also called as trisyl. Now let us first deal with naphthalene in detail. The molecular formula is C10H8. Its chemically IUPAC name is bicyclo 4.4.0 deca 13578 pentene. So it's got 5 double bonds. It's also known by white tar, mothballs, naphthalene, moth flakes, camphor tar, tar camphor, naphthalene, antimite, albocarbon, hexylene in different countries. And this is the exact chemical structure, and you can find there are 1, 2, 3, 4, 5. These are 5 double bonds, so it is pentene. And these are 4, 5, 6, 7, 8, 9, 10 what you can say carbon atoms, so it is deca. So it is a decapentene, and it's bicyclo, so bicyclodecapentene. And if you start counting from there, 1, then this is 3, and then this is, if you start counting, 5, and then this is your 7, and this is your 9. So these are telling you the locations of these double bonds. Okay, fine. Very commonly anybody can see in their everybody's house, these mothballs are there, particularly kept in cupboards to preserve your costly clothes from moths and termites. They give a typical smell. They're also used in the bathrooms and toilets to fight with the bad false odor, and they are a little bit volatile, and slowly they fade away. Also in the form of chips also they are coming. So the molecular weight is 128, appearance is white solid crystals or flakes, and the strong odor of coal tar. It's a very typical naphthalene like odor. Everybody knows how it is, and the melting point is 78. Say for example, naphthalene is a bicyclic aromatic hydrocarbon in which 2 benzene rings are fused to each other at ortho position. These two are ortho position, and the other benzene ring is fused here. And basically this is the counting 1, 2, 3, 1, 2, 3, 1, 2, 3, and these are the 3 canonical forms. Like here the double bonds are 3 double bonds, here there are 2, and here instead of 2 there are 3. Here again the position of the double bond is not matching with this, so these are all 3 different locations of double bonds or the resonance forms, and this 5 double bonds are moving, and therefore this adds to the stability, which is the actual energy is 61 kilocalories lesser than the calculated energy, which is also called as the resonance energy. And it has got the Debye-Huckel rules, 4n plus 2, that is 2 rings are there, so 4 2s are 8 plus 2 10 pi electrons. It is a natural source, is it's obtained from the coal tar fraction of the petroleum oil, and this coal tar is actually very everybody knows it's a black colored semi-solid, and it is used for making roads. We have coal tar roads and we have concrete roads in our country. So this is a coal tar, it's molten, it becomes fluid at very high temperature. It is taken about 200, so it starts distilling. This is a fractional distillation. Up to 200 there is one light oil comes, at about 250 middle oil will come, heavy oil will come, and still above will be a different fraction, that is anthracene fraction. Now for our interest it is the middle oil and the heavy oil fractions. So these are cooled, so you get crystals. These are of course brown color crystals, dirty brown color crystals. They are pressed, so all mother liquor or other impurities will come out, so you get an naphthalene cake. This is again melted and treated with H2SO4 to remove the alkaline impurities, free from basic impurities. It's washed with water. Now it is treated with NaOH, aqueous NaOH, to remove the acidic impurities. So it is it's made free from both basic and acidic impurities. Then it is again washed. So you get almost a pure naphthalene. It is then distilled and it is allowed to cool slowly at room temperature, and beautiful needle shaped, even sometimes transparent to semi-transparent crystals appear, and they are melting 80 degrees centigrade sharp. Let us say the isomerism and nomenclature of naphthalene. Naphthalene, if you start from the right hand side ring, you go clockwise 1, 2, 3, 4. You don't number the junction rings, so you go 5, 6, 7, 8, and then you give 9, 10 to the junction rings. The positions, particularly 1, 4 and 5, 8 are identical. in behavior to various reagents, and position 2, 3 and 7, 6 are identical. So these are named as from the junction, these are alpha and these are beta. So these two are called as alpha. So there are 4 alpha positions in the 2 rings and there are 4 beta positions. The naphthalene, basically chemical elucidation was done, and they proved that it contains of 2 benzene rings fused ortho to each other by strong oxidation and acidic conditions with KMnO4. The one ring opened to give you phthalic acid. That indicates that these 2 COH groups are part of another ring. So, and these are ortho. Phthalic acid is ortho carboxy dicarboxybenzene. So therefore this is ortho fused. This is proved. Further, when they nitrated naphthalene, it gave nitronaphthalene, which again on oxidation gave again nitrophthalic acid. So the oxidation occurred at the other ring, and this again was plenty of supporting evidence to show that this is orthofusion between these 2 rings. So by chemical methods earlier people used to prove that. Now you have so much of spectroscopical methods and even X-ray diffraction and other techniques to show, because this is a very old compound, and that time the spectral or analytical tools were not that developed. So basically a question can be asked, prove how is naphthalene having 2 benzene rings fused in ortho position. So you have to tell simple oxidation, strong KMnO4 oxidation in the presence of H2SO4 from naphthalene to give phthalic acid, which is an ortho dicarboxylic acid. And then you can also take the nitration and then again do the oxidation, and you get the ortho nitrophthalic acid. So these are 2 evidences. Let us see the synthesis of naphthalene, and first synthesis is called as a Howard synthesis. So basically it is benzene with succinic anhydride. This is a succinic anhydride, and this is a classical Friedel-Crafts acylation using AlCl3 as a Lewis acid catalyst, and so you get beta-benzoyl propionic acid, which under the zinc Hg amalgam HCl, this is a typical Clemmensen reduction. So you remove this C double bond, this C double bond, you remove this C double bond, so you get a CH2. So this is, we have seen in aldehyde ketone chapters last year. So this is Clemmensen under acidic condition. Under basic condition you have Wolff-Kishner using hydrogen hydrate and KOH and high boiling solvent like diethylene glycol. Now further it is treated with a strong dehydrating agent. So one H2O is lost, and this cyclizes to alpha tetralone, which is again further subjected to Clemmensen reduction with again acidic condition zinc HgCl tetralene, and then this is oxidized with a warm air with a palladized carbon. This is a noble catalyst under pressure, or you heat it with selenium alternatively, and you lose hydrogens from here. You lose 2 molecules of hydrogen, 2H2, and so double bonds are formed. 2 double bonds are formed. So this is oxidation. So first step, as I told you, is beta-benzoyl propionic acid is formed by a Friedel-Crafts acylation between the reaction of benzene and succinic anhydride in presence of the Lewis acid, and then followed by the Clemmensen reduction. So getting gamma phenylbutyric acid, and then which on heating with a dehydrating agent H2SO4 loses this water molecule to form the tetralane, which is again undergone to tetralone is again undergone Clemmensen reduction subsequent. So 2 times Clemmensen reduction here and here, and you get a you can say cyclohexanobenzene, which is oxidized over selenium or with PDC under pressure conditions using hot air or oxygen, and you get this totally oxidized naphthalene, fully aromatic compound. So that is the synthesis we saw. Synthesis of naphthalene. We have 2 more synthesis of naphthalene. First, this is very classical Howard synthesis, and this repeats again in the other heterocycles. Only the starting materials differ. Either this differs or this differs. So you can say, you give an example of polycarboxylic acid. This is another question. You can ponder on that. We saw it in the earlier slide, so you can understand polycarboxylic acid. Let us say these are the other two syntheses. Second is from 2-phenyl to butanoic acid. The non-saturation is here. So this is butanoic acid, and so this is 2, 3, 4. At the 4 position you got a phenyl ring. So 4-phenyl 2-butanoic acid, a strong dehydrating agent similar like Howard synthesis. So you cyclize this, and now you do a rearrangement. So you get a alpha naphthol. It's a ketoenol type of a tautomerism, and then you do the you can say the dehydrative reaction with zinc at a very high temperature. So this OH is removed, and you get zinc oxide and naphthalene. That is what is here. With zinc dust you heat it, and you remove all this OH. There is a third method, is 4-phenyl 1-butene is the starting material, and this is a butene. So this is 1, 2, 3, 4, and at the 4 position is phenyl. So 4-phenyl 1-butene. Butene is here 1, and this is simply is passed over the vapors of 4-phenyl 1-butene, which is a liquid and which is a hydrocarbon, are vaporized and passed over very red hot cuprous oxide, and you get cupric oxide, and you get naphthalene. So basically, let us summarize all the 3 syntheses: Howard synthesis, 4-phenyl 2-butanoic acid synthesis, and 4-phenyl 1-butene synthesis. And we will go for a summary of this synthesis. Let us see the first synthesis once again. Let us recapitulate it. So this is your first synthesis, benzene plus succinic anhydride, classical Friedel-Crafts acylation. So you get the corresponding acid, and this is under Clemmensen reduction. This carbon is reduced, and then this is dehydrated. H2 is gone, so you get this tetralone. Tetralone is again Clemmensen reduction, so this is gone, and then you oxidize it. The second synthesis is again simply dehydration, rearrangement to alpha naphthol, and heating it strongly with zinc dust, you get this. And this is simply the vapor of 4-phenyl 1-butene over red hot cupric oxide, you can say cuprous oxide, sorry, you get naphthalene. It's very easy to remember this. Naphthalene, let us see the properties, and it's a resonance hybrid. Naphthalene is less aromatic than benzene, and therefore is slightly more reactive than benzene, and electrophilic substitution reactions occur faster compared to benzene. And most important is all hydrogen atoms are not equivalent like benzene. Benzene, all 6 hydrogen atoms are equivalent, so we don't call 1 chlorobenzene, 2 chlorobenzene, 3, everything is monochlorobenzene. But here it's not like that. Here we have a little bit a difference of the derivatives, and therefore you have alpha position and beta position. You have alpha hydrogens and beta hydrogens which are not equivalent. The resonance hybrid of the sigma complex for the sigma attack, alpha attack, is found to be more stable than the resonance hybrid of. So the attack is more preferential at the alpha position than the beta position, and this is the alpha attack. So this is alpha, 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 and you can see there are 7 resonance hybrids, resonance structures. Compared to this, at the beta we have got only 6, so there it scores. And further, so it is more preferred at the alpha position, 7. So the electrophilic substitution naphthalene occurs mostly at the alpha position. Next is orientation of substitution. Further, a deactivating group directs the electrophile to take a position in the second ring because the availability of the electrons in the first ring is reduced. So if already a electron withdrawing and deactivating group is there, it has sucked electrons from one ring, so naturally the electrophilic substitution will not occur in that ring, but it will occur in the adjacent ring. It's very logical. For possible addition products at the 3, 4, 5, 6 position to a naphthalene bearing an electron withdrawing group, that is EWG, at alpha position, it can be seen that the two cations avoid a direct destabilization by the electron withdrawing group, while this is not the case when this EWG is attached as a position 4 and 6, which shall lead to resonance destabilization. Therefore, the effect of EWG is to favor addition at the following two positions, that is at the 3 position and at the 5 position. Okay, so let us see at the 3 position and at the 5 position. But okay, look, the products in the above example, that E group is attached, added at the third and fifth carbons away from the electron withdrawing group. So first, second, third carbon, fourth and fifth. Exactly the relation as the two meta positions in a monocyclic compound. So had this been here, forget this. So this EWG group was actually one carbon more. So had it been here, this is 1, 2, 3. So had it been in the mononuclear, it is meta, and had it been here, it is again meta. So this is exactly like benzene. So electron withdrawing group is a meta director group. It is not the what you can say ortho position. Had it been here, it would have been ortho position here, or it would have been here. This is out of question, of course. Okay, this is out of question. So this electron withdrawing group goes at the third and 5 position, and it does not go at the other positions. Okay, neither it goes at the 4 position or 6 position. Had it been here, it would have been para position, this would have been para position. There is no question of going at the junction position, so it goes to the meta position. This is almost like you had this group at here. So this is meta, this is meta. Nicely explained. Okay, fine. So here is the actual example of electron withdrawing group. What happens when you have got an electron donating group? So EDG, and they are ortho-para-directing in the benzene. They are also ortho-para-director in the polycyclic, and the first ring where the electrons have been pumped and activated will be more ready for electrophilic substitution. So there are difference when electron withdrawing group is there, the always substitution will go, next substitution will go to the adjacent ring because the first ring is depleted of electrons. But in case if electron donating group is there, it will substitution will occur at the same ring and preferably at the ortho or para position. So in benzene it will be always ortho and para position. So this analogy, it will also go to 2 and 4 position and in the same ring. So with amino group, this is nicely explained. An activating group at one position directs an electrophile to the 4 position preferentially and to a certain extent to the 2 position. If such a group is present as position 2, it directs the electrophile to take position 1. Had this group been here, it would have directed here or here, not here. Okay. So this will of course always direct here and here, more preferentially here, but had it been present here, it would have directed here. Let us see various chemical reactions of naphthalene can be oxidized to varying degrees by subtle use of reaction conditions and reagents, leading to oxidation under different conditions. This is chromium trioxide in acetic acid. It will give you just ring oxidation. So naphthaquinone. If you go for a drastic one like KMnO4 and H2SO4, it will break the ring to the phthalic acid, and if you go still further, it will go further dehydrate it to phthalic anhydride. So you get 3 different products. There is another reaction called as ozonolysis, which falls under the category of oxidation, and we have seen this in alkenes. So similar to alkenes, the 2 double bonds will get added with 2 ozone molecules. This is a monoozonide, diazonide, then becomes monoozonide, and then it breaks open to give you the carbonyl compound formaldehyde, diformaldehyde, or this is the phthalaldehyde. Then next comes is the reduction. Partially can be reduced to complete reduction, varying degrees of reductions. Like if you use simple sodium metal in ethanol, you will get just one double bond will be reduced. But if you go for a higher alcohol like isomyl alcohol at 132 degree, this entire ring will be reduced and you will get tetraline. But if you go with a catalytic hydrogen in the presence of noble metal like platinum or any nickel, you will get a complete decalin. So this is a tetrahydronaphthalene, this is decahydronaphthalene. Both rings are reduced. So you get dihydro, tetrahydro and decahydro derivatives under varying conditions of reagents and the reaction conditions. Next is a halogenation, of course. So chlorination of naphthalene using simple sulfuryl chloride can lead to a product mixture of 1-chloro and 2-chloronaphthalene when it is used in equimolar proportion. But if you use it in double the quantity and at a higher temperature, like a refluxing, you get 1,4-dichloronaphthalene. Bromine is bit specific, and if you go with a bromine in carbon tetrachloride at room temperature, you will get only monobromonaphthalene, 1-bromonaphthalene. But if you increase the proportion to 2 moles, then it will go to the 1,4-dibromonaphthalene. Nitration again, with a simple nitrating mixture at 60 degrees temperature, you will get 1-nitronaphthalene. But if you further do the nitration at higher temperature, it will also go to the other ring 1,5-dinitro, and you will get a mixture of 1,5 and 1,8-dinitronaphthalene. And this is 2, 3, 4, 5, 6, 7, 8. So this is 8 and this is 5. Sulfuration has always been a typical thing, and with a simple sulfuric acid and with 80 degree temperature, this can be fuming sulfuric acid, of course. You will get alpha sulfonation and you get naphthalene 1-sulfonic acid. But if you increase the temperature, make it more drastic, it becomes a beta sulfonic acid or naphthalene 2-sulfonic acid. Higher temperature leads to beta position. Chloromethylation, that is under the formyl conditions with formaldehyde and HCl combination and acetic acid, you get the 1-chloromethyl naphthalene derivative. With the classical formaldehyde conditions of formaldehyde and HCl in acetic acid. But if you do for the further electrophilic reactions like electrophilic substitution reactions like Friedel-Crafts reactions, and if you go for the Friedel-Crafts acylation reactions, if you use it mild conditions like CS2 or you can say dichloroethane, lower boiling solvents at lower temperatures with of course the Lewis acid catalyst and the acetylating agent, you get the one expected one acetyl naphthalene. But if you go to a higher boiling solvent like nitropentane, it will go to the beta position or 2 acetyl naphthalene. Friedel-Crafts alkylation with a simple methyl iodide, you will get a product mixture of 1 methyl naphthalene and 2 methyl naphthalene, but with ethyl bromide you will always get it at 2 position, beta position, which is little bit not the expected one. So I have tried to summarize these reactions. So like with simple oxidation of naphthalene, you get a product mixture of first just the naphthoquinone, then phthalic acid, then phthalaldehyde, and if you further go with vanadium pentoxide, you get a phthalic anhydride. With reduction, of course, you will get dihydro, tetrahydro, decahydro. Okay, I'm sorry, actually this is totally reduced. And with nitration, you will get, of course, with two different derivatives. One will go at 5 nitro and one will go at 8 position. But if you do the nitration at a lower temperature, you will get mono nitro. With sulfonation under normal conditions, with fuming H2SO for 80 degree, you will get the alpha sulfonic acid, but with higher temperature, you will get beta sulfonic acid. Halogenation in normal conditions with sulfuryl chloride, when you use, you will get a product mixture of expected alpha chloro, but if you exceed it, you will get 1,4-dichloro. But if you increase the temperature, higher temperature, then you will get the beta chloro. Bromine is little bit more specific, and with the equimolar quantity you will get a monobromo at alpha position, but with the double quantity you will get 1,4-dibromo. As far as alkylation is concerned, with methyl bromide you get a product mixture of alpha and beta, but with ethyl you will get always beta, which is little bit unexpected. With acylation, if you do the normal CS2 condition, you will get the alpha acetyl, but with nitropentane at higher temperature, you will get beta acetyl. With classical formulating conditions, you will get the classical expected 1-chloromethyl or alpha chloromethyl naphthalene, and this is nicely summarized. This is a summary of the reactions. Fine. Orientation of substitution we have seen. With naphthalene you generally get, here it is expected, here it is expected, here it is expected. With what you can say higher temperature or changing the boiling point, you get this. Normally you get this, but with higher temperature it shifts here. There are certain derivatives, some naphthalene derivatives. Simple is alpha naphthylamine, and like benzene you convert it into nitronaphthalene like nitrobenzene, and then reduce it with iron HCl, so you get 1-amino naphthalene. Two-step nitration and reduction process is there. You can also make these under pressure conditions from 1-naphthol and ammonia in zinc chloride in a sealed vessel at a very high temperature. This will be a nucleophilic substitution of the OH with NH2. On similar lines, beta naphthol with ammonia under acidic catalysis will give you the 2-amino naphthalene. Fine. Further derivative is alpha naphthol, that is again like phenol. You make the sulfonic acid, you make the sodium, you treat it with solid NaOH, cook it with solid NaOH to get a sodium salt, and then further with solid NaOH at higher temperature you get the sodium phenoxide. and then that you hydrolyze, you get the corresponding phenol after acidification. This is a very conventional method like benzene, and we get the from starting with naphthyl to sulfonic acid. You can get beta naphthol also, same method, only position is beta. So you start with the beta sulfonic acid or 2 sulfonic acid. They can also be naphthoic acids are obtained from the corresponding acetyl naphthalenes. This is a typical hypoiodide oxidation, basic hydrolysis, and you get the corresponding compounds. Let us see the applications. The chemical intermediate used for industrial production of phthalic anhydride or other naphthalene derivatives like alkyl naphthalenes, sulfonates, surfactants, the insecticides like 1-naphthyl N-methyl carbamate called as carbaryl, naphthols as well as naphthene sulfonate polymers. So it has got a wide application in making chemical intermediates, but it's also widely used as a fumigant for household as uses for as a moth repellent, and the naphthalene pellets are very commonly used, and their vapors are create a toxic level to the larvae of many moths which attack the textile. It's also used as a fumigant in the soil, pesticide, and attic spaces to repel animals and insects, and in particularly in the museums it finds a lot of importance. Storage drawers and cupboards to protect the content from attack by insect pests. Is a repellent to opossums and could be used to deter them from taking up residency in people's homes. Opossums are a real great nuisance. Naphthalene sulfonate polymer plasticizers or dispersants are used to produce concrete and plaster boards, like for wall boards or drywalls. They're also used as dispersant in synthetic and natural rubbers and as tanning agents in leather industry, agricultural formulations, dyes, and as dispersants in lead acid battery plates. They're used as wetting agents and surfactants in textile and fabric industry as alkyl naphthyl sulfonates like ANS, which are short formed, are used in as non-detergent wetting agents to disperse the colloidal systems in aqueous media for bleaching and dyeing operations. It's also used for the manufacture of dyes, explosives, and synthetic agents, and particularly in the perfumery industry. The methyl and ethyl ethers of 2-naphthalenes, which are commonly called as the ethyl and methyl ethers, are called as nerolines. They used to be used as in the perfumery industry. The naphthalene is also solvent for chemical reactions in the molten state. It's excellent solubilizing agent for hydrocarbon or aromatic compounds. It can be also used as a high boiling solvents like dichlorobenzene, benzonitrile, nitrobenzene, and durine. And it is a niche application in pyrotechnic special effects such as generation of black smoke in simulated explosions. So in warfare also it is useful. So this is a depiction of the various uses of naphthalene. And dear friends, this is as a plasticizer, as dyes, as wetting agents, as fumigants in perfumery, in as intermediates, very useful intermediates we have seen. And therefore I think you enjoyed this lecture, and thank you very much. Next time we will move to the another video where we will discuss anthracene.